All right, yeah. So thanks, Sakib, and thanks a lot for the invitation to speak here today. And I guess my talk today brings more of an academic perspective to the theme of the meetup today. Um, and yeah, and I think I'm going to be talking about a lot of things that kind of connects to what Aiden was talking about: pose estimation and generating models and so on. So I thought a little bit about what I should title my talk today, given that the theme of the meetup was deep learning for gaming, and I kept a fairly naive or fairly simple title of deep learning for gaming. But then I wanted to make sure at the very beginning that I'm clear on what are the things that I'm going to be talking about, because as Aiden mentioned, I think there's a lot of different connotations when we say AI. And AI can mean anything from a bunch of if-then statements to complex machine learning models, neural networks that learn really interesting things. So the title for my talk today is 3D deep learning for gaming. And this 3D is quite important, as you'll probably see when I talk a little bit more about some of the work that we've done. But very specifically, if I can get my mouse on the display, there you go, yeah. So yeah, very specifically, what I'm going to be talking today is actually 3D computer vision for gaming. And when I mean computer vision, it's mostly about using images to understand our environment, and we rely on a lot of deep learning tools and techniques to do that. So I'll be talking about 3D computer vision techniques for quote unquote gaming. And the reason why I have this in quotes is that to me, gaming, when I say gaming in this talk, I really mean computer graphics. And computer graphics spans all kinds of different modalities. So you can think of visuals, you can think of audio, you can think of path planning. Different aspects of gaming are kind of included in computer graphics, and of course interactive techniques. So how do we use our hands to interact with VR, AR devices, and so on and so forth. So I'm personally a computer vision researcher, but I've been kind of watching the SIGGRAPH community. So SIGGRAPH is one of ACM, the Association for Computing Machineries, interest groups, special interest groups for computer graphics and interactive techniques. So the theme of my talk really is going to be, how do we develop, what are the examples of tools that we've developed for 3D computer vision that can be used in game. I'll be spending most of my talk on describing some of the techniques that we've developed. So these are, state-of-the-art machine learning research tools. But towards the end of my talk, I also want to talk a little bit more about the inverse of 3D computer vision for gaming, which is really gaming for 3D computer vision. So I think that the central theme, the takeaway message that I want to convey in this talk is that 3D computer vision is not really just a tool for gaming. It's not a one-way street, but it's actually a two-way street. We can use 3D computer vision for gaming, and gaming can be quite useful for 3D computer vision. And I'll talk a little bit more about what I mean later in the talk. So I see that the time is 7:10, so I'll try to wrap it up maybe a few minutes after 7:30, if that's okay, Sakib.
Yeah, that's good.
Okay, great. All right, so let's dive into it. So, as we all probably know, we live in a diverse 3D world, right? So we go to a supermarket, we look at vegetables, pick them up, inspect them before we purchase them. We build large infrastructure with machinery. We use our hands to interact with the world around us, cooking, woodworking, and so on. So all of this, these examples show that we live in a very rich 3D world, right? So we move about in a 3D world in 3 dimensions. We kind of use our hands to interact with the 3D world. We manipulate objects, we grasp objects, and so on and so forth. One of the goals of computer vision is to be able to observe these kinds of natural human behavior in a 3D world, and to really understand how humans behave in 3D worlds and how the 3D world looks like. And this is useful, especially in gaming, because we want to kind of enable richer gaming experiences. One example of that is virtual reality, augmented reality, and mixed reality in general. So we want to create virtual worlds where we can interact with the virtual world in a very immersive way, in a very rich way, and in a very interactive way. So we want to be able to manipulate the virtual world, be it in virtual reality, be it in augmented reality, or anywhere between the spectrum in between these two things. So that's really the goal. So the goal of my research is to kind of observe the world and to be able to visually understand how we can create virtual worlds and interact with the virtual world by observing the real world. So that's at a very high level the goal of the research that I do. Now, this is actually quite a difficult problem from a computer vision machine learning perspective, because as I said, the real world is in full 3D. So there's 3 dimensions to all objects in the world. The real world is dynamic. Things move about in the world. Things collide. Objects collide with each other. And also the real world is diverse. So, if you talk about cars, there's thousands and thousands of different varieties of cars. So we have sedans, we have SUVs, and so on and so forth. So really, from a computer vision perspective, the challenge is how do we make computers understand what they're looking at, what they're observing in images and videos. And this is really important because unless we do this, it's very difficult for us to create virtual worlds that mirror the real world. So my talk today is going to be roughly split into 2 parts. The majority of my time I'm going to be spending on showing you examples of some of the research that we've done in developing 3D computer vision techniques, which can eventually be used for computer graphics applications, for gaming applications. And towards the end of my talk, I'm kind of going to flip the coin, right? And I'm going to talk a little bit about how computer graphics and gaming techniques can be used to develop 3D computer vision techniques. And when we talk about 3D computer vision techniques, I'm kind of going to roughly split this into 2 categories, right? As I mentioned, the real world is interesting because as humans, we are able to move about in the real world and interact with things. So I'm going to be talking about how we can have computers understand humans. So that's 3D visual understanding of humans, and how we can have computers understand objects. So that's 3D visual understanding of objects. And again, this connects to many of the things that Aidan was talking about in his talk, especially with human pose estimation and so on. Let's start by looking at 3D visual understanding of humans. Now, as I mentioned, humans, we interact with the world in complex ways through our bodies. So we move about in the environment, we move about in the kitchen, we use our hands to make things. So we might use our hands to make circuits, we might use of our hands to make pasta. Our hands are really important to the way we interact with the world. So one of our goals is to be able to understand humans, both in terms of their full body posture, as well as hand posture from images and videos. So let's look at full body posture, understanding full body posture. This is often referred to in the research community as articulated human pose tracking or articulated human pose estimation. And there's been a lot of really great work that has been done in this area. You might have all heard of the Microsoft Kinect, which was one of the most successful gaming devices from Microsoft, which is essentially a depth sensor. And this depth sensor is capable of figuring out the posture or the articulation of a person standing in front of it. And there's a bunch of work that tries to develop these techniques and come up with new techniques for doing human pose estimation. However, these approaches do have some limitations. Many of these approaches are limited to 2D. So they have a very good understanding of where a person is on an image, but not quite in the 3D world. And as I said, understanding humans in the 3D world is quite important. Many of them are depth sensor based, for example, the Kinect. And depth sensors are not exactly commodity hardware. I mean, you can buy it off the shelf, but they're still much more expensive than RGB web cameras like the one that I'm using right now. Many of these methods lack generalizability. So they don't work outdoors. For example, depth sensors don't work outdoors because sunlight interferes with the way these sensors work. So there's a bunch of limitations with using existing work. So what we were really looking for is a solution that uses off-the-shelf web cameras, but still provide us with information about 3D articulation of humans in the world. And I'm talking about full body articulation, so where the person is, how the person is moving. So yeah, the goal is, given a single web camera that you can just buy off the shelf, we'd like to estimate the full 3D posture of people in the frame of the image. So we developed a technique, and as my title alluded to before, this technique uses deep learning. And the idea is that we have input from a web camera, like what you see on the left. And we have a neural network. The particular details of the neural network are not too important, but essentially we have a ResNet 50 convolutional neural network architecture. And what this architecture does is it's able to predict two outputs. So it predicts where the joints of a person, so for example, where the elbow is, where the head is, and where the torso is, and so on, both on the 2D image as well as in 3D. So it tries to predict the locations of these salient joints on images and videos. So we have this neural network that does this task, but then this does it only for a single image. So if you have a video sequence or live stream, like what you're seeing right now, I'm moving in this video sequence. So what you really want is to have a temporal understanding of how a person moves. And to do that, what we do really is we take the video and split it up into a bunch of frames. And for each frame, we apply our neural network to get the position of the joints in 2D as well as the positions in 3D. And then we have a temporal post-fitting step where we use inverse kinematics. And I don't think I have to explain what inverse kinematics is because I didn't help me with that. But essentially, we take these 2D and 3D key points that the neural networks predicts, and we're able to fit a temporally smooth skeleton, which is quite useful in computer graphics. So if you have a character, a virtual character, a virtual avatar of yourself, then you can kind of use the output from our neural network to directly retarget and control this virtual character. And that's really the final output of our method. So here's an example of our method working in real time using a single commodity web camera. So as the person moves, the virtual character, which you see on the left, a stick figure here, moves exactly like the person. So essentially, the motion of the person is being retargeted to a virtual character in real time. So as I said, this uses a single RGB camera, and it works for diverse scenes and subjects, as I'm going to show momentarily. And it's really fast. So here are more examples that showcase the diversity of different people, different clothing, different environments, different camera positions that our method is able to accommodate. And as you can see, it's robust to fast motions. Even if it does fail for a few frames, it does recover very quickly. And one thing that I should note here is this is work that was done almost 3-4 years ago now. My colleagues have done a great job in kind of improving this method to support multiple people, making it even faster and even more accurate and robust. So you should definitely check out the homepage of this project for more details and code and data sets. So what are the gaming applications of this kind of technique, right? So one application is that we can replace the Kinect. So we can take a depth sensor, replace it with a RGB sensor, and we can have full human pose estimation based on a camera. So in this case, we have a camera that is external, looking at the person, and we are using this to drive a virtual character, both in VR as well as in a normal game. And you can kind of do this using mobile phone cameras as well. So in this case, the video from the smartphone is being streamed to a computer where we run our neural networks, and we're able to control a virtual character in real time using this pipeline. And of course, because we don't require hardware which is specialized, we can run this on YouTube videos as well. So we've been able to run this on videos of footballers and babies and so on and so forth. So that's just a very quick overview of how we've developed techniques that can potentially replace markers, like what Aiden was showing and was doing at his startup, but with just video cameras, which are commercially available, off the shelf, and are quite inexpensive. And we're able to kind of track the pose of the person in real time. But as I mentioned before, the way we interact with our world is through our hands. And hands play a very important role in how we manipulate objects and how we interact with the world. So we've also developed similar techniques that uses a single RGB camera to estimate the 3D pose of hands. And here is an example of some of this work from a couple of years ago. Okay, so what I've talked about now is how 3D computer vision can be used for graphics. And I've shown how visual understanding of humans can be, we can do this from images and videos. Another aspect to how humans interact with the world is objects. So the real world has a lot of different kinds of objects. And sometimes we might want to populate the virtual world with objects that we see in the environment. So if you see a nice car, you might want to have this car in your virtual world. So I'm also going to talk a little bit about how to develop an understanding of objects that we see in the world through images and videos. And as I said, you might have an environment like this, which is your home office, and you might want to replicate it in virtual reality. And in order to do that, you need to reliably reconstruct objects that you see in your environment. So you need to be able to take multiple images of your object and be able to reconstruct a 3D model of your object, which you can then place in your virtual environment. So what we're trying for here is to develop a technique that can enable this for end users, right? So you have your smartphone camera, you have an object of interest, you click a few pictures of this object of interest, and you instantaneously have a 3D model of that object, which you can then place it in your game or in your VR environment and so on. So once again, deep learning to the rescue. And I'm kind of, being a bit hand-wavy about the exact techniques that we use. I think there's a lot of interesting bits in the deep learning neural networks that we use. I'm happy to talk about this offline. But for now, I'm just going to say that we have yet another neural network architecture, which takes in the images that I talked about. So you have your smartphone camera, you click 5 images of an object of interest. So in this case, a car. And what the network outputs is it outputs a 3D reconstruction as a point cloud. So essentially a bunch of points, bunch of 3D points that represents the shape of the object. But there was one limitation with what we were trying to do here, which is that we were reconstructing the object as a point cloud, which is just a bunch of 3D points, right? So this is not really something that we can use in games or computer graphics because it does not have the visual fidelity and quality that we often expect from games. So what we really wanted was a high quality mesh, parametric mesh reconstruction, which we can then use in games, which is nicely textured and so on. So again, I'm not going to go into the details here, but essentially we have a more complicated neural network, if you will, which has this capability of taking input images and somehow lifting 3D information out of 2D images. So we have this neural network that essentially learns how to flatten out 3D shapes. And then once it's flattened that out, it can reassemble them to a 3D shape. And again, I'm not going to go into the details here, but I'm very happy to talk about it offline. But I'm going to jump into some very interesting results. So what you see here is a reconstruction of this car, which is completely unseen. So the neural network has never seen this particular car before. All that it's given as input are the 5 images that you see on the top. So the 5 different views of the car from the top. So you click like 5 pictures of your favorite car, and what the network outputs is the 3D model that you see on the bottom. No camera calibration information is required. No extra information is required. So that's the only thing that is required. And as you can see, this model, although not quite to the level of quality that you would expect if this were handcrafted, is still, I would say, a very reasonable quality, given that this was generated fully automatically. Even the texture information, the color of the individual parts of the car are lifted from the image. And this is work that is going to appear at the European Computer Vision Conference this month. Okay, just as an aside, because we are talking about gaming, many of you might have heard of Microsoft Flight Simulator 2020. And I just wanted to put in a video of the game here because some of the visuals here are really stunning. The last time I played games was over 15 years ago. And the release of this game has kind of motivated me to try gaming again. And I've already pre-ordered it and I'm looking forward to trying it. But I think what's really interesting, and the reason why I show this video here, is that they use many similar, I don't know what exactly they do, but my understanding is that they use machine learning techniques in order to generate many of the assets that you see in this environment. So the trees that you see on the left, some of the buildings that you see are all generated by machine learning algorithms. I just want to point out that the method that I talked about earlier for reconstructing cars is a similar method, right? So you could eventually think of creating assets for your game using machine learning techniques like what we've developed. Great. So what I've talked about so far, it's kind of a really whirlwind tour of the state of the art in computer vision. And I'm mostly focused on work that we've done in our group at Stanford with our collaborators. And there's a lot of really great work that others in the computer vision community have been doing, many of which have really short-term applications in game. And what I've really provided you is a very small sneak peek of some of the work that we've done. And I really encourage you to look at the related work in some of the papers that I mentioned today in order to get a sense of where the computer vision state-of-the-art research currently lies. Now, in the last 5 minutes of my talk, what I want to do is to kind of take a step in the reverse direction. So I mentioned earlier that most of my talk today is going to be focusing on 3D computer vision for gaming and computer graphics. But it's not a one-way street because we computer vision researchers have a lot to benefit from the state-of-the-art tools and techniques that have been developed for gaming. And let me explain why that is the case. Now, if you think about what computer vision is, really computer vision is about taking images of the world and trying to create a representation of the world from the images. So you can think of creating a model of the real world through images that you take on the left. And what is computer graphics? Computer graphics is really the inverse process, right? So you have models and assets of the world, and you're trying to create images from it. So really, computer vision and computer graphics are two sides of the same coin. And therefore, it makes total sense to say that if I claim that 3D computer vision can be useful for computer graphics, the inverse has to be true. Computer graphics has to be useful in developing and making 3D computer vision much better than what it is today. So again, just to kind of flip things around, right? So what we now have is graphics for 3D computer vision. And I'm going to show just a brief glimpse of some of the work that we've done on creating synthetic humans to develop 3D computer vision models or 3D computer vision techniques for detecting humans and creating synthetic object images which can help us detect objects much better. So let's look at synthetic humans as an example. So I'd like to take the example of hand pose estimation. So hand pose estimation refers to the problem of figuring out the joint locations of the fingers in the human hand as we move our hand in a video. And one of the things that we tried a few years ago was it's very difficult to obtain training data for training machine learning models that do hand pose estimation. And I should mention that all of the machine learning techniques that I talked about earlier are supervised machine learning techniques. So they require training data which has input images and ground truth labels. So labels for the 3D locations of the joints. And it's notoriously difficult to obtain this kind of data for hands. And I think that's why you see a lot of people using motion capture suits because they make this task a little bit easier. So what we tried to do here was to develop a simulator, essentially, a game, if you'd like, where the game only consists of one hand grasping different kinds of objects. So we have this game, which was built entirely in Unity. And the idea here is we want to simulate different postures of the hand, grasping different kinds of objects, and use this to train our machine learning models. And that's exactly what we did in our ICCV paper a couple of years ago. And the advantage of doing that is that we get free labels. So the labels that we get have ground truth information, which you can then use to train your machine learning models. And of course, we can generate depth images. And so we have a lot more control over the data generation process. So here's an example of how we collect this data. So we have essentially a hand tracker, which has been previously trained using a different method. And then we kind of ask people to grasp different kinds of objects in a game. So what you see on the screen there is essentially a game. And we then use this game to simulate more and more examples of hands with different skin tones, different postures, different objects, different backgrounds, and so on and so forth. So we are able to kind of exponentially grow our training data using methods like this. I'm going to skip through this because I think it's not too important. And I'm going to talk a little bit about synthetic objects for 3D computer vision. Now, the more observant of you might have noticed that, when I showed you examples of reconstructing this car, many of those images were actually not real images. They were images of synthetic cars. So they were images of virtual cars. Because the machine learning method was trained on virtual cars. So we kind of created a repository of 3D car models, and we trained our machine learning model and tested it on this repository of virtual car models. And one of the techniques that we use for generating this kind of data is what we call context-aware mixed reality. And this is very interesting because we want to create data which looks as similar as possible to real data. And to do that, what we do is we actually went to IKEA, believe it or not. And the reason why we went to IKEA is that, if you've ever been to IKEA, you know that IKEA has a lot of different kinds of mock rooms in their showrooms. And the interesting thing is the tables that they have in these mock rooms don't have any objects on them, which means that we can then place synthetic objects on top of these real tables. And then we can generate synthetic data that looks much more realistic than if we generated the whole data using a synthetic rendering pipeline. So we went to IKEA, we captured a bunch of tabletop scenes, and then we put like virtual objects on top of the tables that we found in IKEA. And then we are able to kind of generate ground truth supervision for these machine learning models that we subsequently train. And yeah, so here's more examples of some of the data that we generated. So you can see that you have all these different tables, and then these coffee mugs and laptops are kind of laid out in a more realistic way than if you rendered the whole thing in a gaming pipeline. And again, all of this is running inside Unity. So we essentially built a Unity game that does the whole thing. So yeah, I think the moral of the story here is that we've benefited tremendously from many of these computer graphics pipelines that have been developed over the last several years. And I think it's a two-way street. So what we can improve our state-of-the-art 3D perception, 3D computer vision algorithms by relying on traditional computer graphics gaming pipelines. Okay, so just to conclude my presentation, I started off by talking a little bit about 3D computer vision for gaming. And I talked about some of the state-of-the-art techniques that we've developed for understanding humans, how humans move, how hands move, and being able to reconstruct objects in a very realistic way so that we can put these objects in VR environments, in games in a much more realistic way. But then I also talked about the inverse of this problem, which is how we are relying on games and game engines to improve our 3D computer vision algorithms. And I think there's still a lot to explore in this area. And I think Unity and many other companies out there are kind of investing more in this area. And I'd like this to kind of, I'd like to see this being pushed forward in the future. All right, so with that, I'd like to conclude my talk. I'd also like to take this opportunity to thank my collaborators. All of the work that I talked about today was a collaborative effort with lots and lots of people. Yeah, so I'm happy to take any questions. I'm sorry for running a few minutes behind schedule, but I'm very happy to take any questions now.